From Earth to nearly 96,000 kilometers above the planet, engineers have envisioned a transportation system unlike anything ever built. At this scale, gravity, atmospheric forces, and orbital mechanics create one of the greatest challenges in modern engineering. How can a single ribbon connect Earth directly to space? The answer begins not with rockets or steel, but with a material engineered one molecule at a time. And that journey starts inside a precision manufacturing facility where the first carbon nanotube ribbon is created. Everything begins with a material strong enough to support a structure stretching 96,000 kilometers into space. Inside precision reactors, carbon atoms assemble into continuous nanotube ribbons with extraordinary strength and remarkable consistency. Each newly formed ribbon is carefully inspected, ensuring even microscopic flaws never become part of the future tether. As production accelerates, thousands of meters of reinforced ribbon are prepared for one of engineering's greatest challenges. These massive spools become the backbone of a structure designed to remain under constant tension from Earth to orbit. But manufacturing alone changes nothing. The next challenge is building an ocean platform capable of holding the world's first space elevator. The entire space elevator depends on a floating platform positioned with extraordinary precision along Earth's equator. Powerful tension leg foundations keep the massive structure remarkably stable despite constant waves, currents, and changing ocean conditions. Automated ballast systems continuously rebalance thousands of tons of seawater to maintain perfect structural alignment. Far below the surface, robotic inspectors verify every seabed connection, supporting the immense forces above.
All stop forward momentum. Hold station for transfer. Crane 2, you are clear to lift.
This offshore platform becomes the permanent gateway between Earth's surface and humanity's future route into space. With the anchor secured below, construction can finally begin where gravity starts to lose its grip, in low Earth orbit. Before the tether can descend, engineers must first construct a permanent assembly hub orbiting hundreds of kilometers above Earth. Autonomous robotic systems assemble enormous titanium frameworks with extraordinary precision in the weightlessness of low Earth orbit. Space-grade laser welding creates seamless structural connections capable of enduring constant thermal cycles, and orbital stress. Ion thrusters make continuous adjustments, keeping the entire construction platform perfectly aligned as Earth rotates below. Once completed, this orbital hub becomes the gateway where equipment, materials, and the future tether are brought together. But this station is only the beginning. The true control center must be built much higher in geostationary orbit. At 36,000 kilometers above Earth, the entire space elevator reaches its most critical point of balance. Precision thrusters continuously correct orbital drift, allowing the station to remain perfectly fixed above the equator. Robotic construction systems expand the central hub into a permanent logistics center, supporting every future operation. Power, communications, and structural stabilization work together to maintain continuous control throughout the enormous orbital complex. From this fixed position, every component of the elevator can be monitored, supplied, and precisely coordinated. Only one element remains unfinished: the massive counterweight that will keep the entire structure permanently under tension. Nearly 96,000 kilometers above Earth, the counterweight provides the outward force that keeps the entire elevator under constant tension. Powerful plasma-tug spacecraft carefully position the massive asteroid before permanently locking it to the outer terminal station. Robotic systems continuously monitor structural loads, while precision propulsion maintains perfect balance against changing orbital forces. Together, the asteroid and orbital station create a stable counterweight capable of supporting one of humanity's largest engineering structures. Only after this balance is achieved can the space elevator safely extend toward Earth's surface without collapsing under its own weight. Now the first ultra-thin pilot tether begins its long descent from orbit toward the waiting ocean platform below. The fragile pilot tether is only the beginning. It must now be transformed into a structure capable of carrying enormous loads. Autonomous reinforcement climbers continuously add new carbon nanotube layers while steadily ascending the growing ribbon.
We have a tension spike. Check alignment now. Adjusting parameters. It's stabilizing.
Advanced laser fusion systems permanently bond every layer into a single continuous structural element with exceptional strength. Ultrasonic inspection systems verify each completed section before the climbers continue reinforcing the next segment. Gradually, the microscopic pilot tether becomes a meter-wide ribbon capable of supporting future transport vehicles. With the structural ribbon complete, the next challenge is delivering enough energy to power every climber traveling into space. The fragile pilot tether is only the beginning. It must now be transformed into a structure capable of carrying enormous loads. Autonomous reinforcement climbers continuously add new carbon nanotube layers while steadily ascending the growing ribbon. Advanced laser fusion systems permanently bond every layer into a single continuous structural element with exceptional strength. Ultrasonic inspection systems verify each completed section before the climbers continue reinforcing the next segment. Gradually, the microscopic pilot tether becomes a meter-wide ribbon capable of supporting future transport vehicles. Engineering diagnostics confirm every reinforced layer meets structural specifications before the climbers continue upward. With the structural ribbon complete, the next challenge is delivering enough energy to power every climber traveling into space. Unlike conventional spacecraft, elevator climbers carry no fuel and receive all of their energy directly from Earth. Powerful phased array laser systems transmit concentrated energy upward while maintaining precise alignment with the climbing vehicles. Adaptive optical systems constantly correct atmospheric distortion, keeping the laser beam stable over extraordinary distances. Orbital relay mirrors extend the energy path, delivering uninterrupted power far beyond Earth's atmosphere. With power flowing through the entire network, the first robotic climbers are finally ready to begin their ascent. The completed ribbon is finally ready to carry its first robotic climber from Earth toward orbit. High-torque ceramic rollers grip the ribbon securely, while electric motors deliver smooth and continuous upward motion. Laser energy received through photovoltaic panels powers the climber without requiring onboard fuel or rocket engines. Engineering systems constantly monitor traction, temperature, and structural loads throughout every stage of the ascent. After a flawless journey through the atmosphere, the climber proves the space elevator can transport cargo safely into orbit. The final challenge is protecting this enormous structure from the constant threat of orbital debris. Protecting a structure stretching 96,000 kilometers requires continuous monitoring across both Earth and space. Radar stations and orbital sensors constantly predict debris trajectories long before any collision can occur. When necessary, the offshore platform performs controlled repositioning, allowing the entire ribbon to shift safely away from danger.
The deflection rate is increasing on Tether 3. Reroute power to stabilization immediately.
Active stabilization systems immediately absorb vibrations, keeping the enormous structure perfectly balanced after every maneuver. Working together, these protection systems keep the space elevator operating safely, despite the constantly changing orbital environment. From a single carbon nanotube fiber to a permanent transportation corridor, the space elevator becomes one of humanity's greatest engineering achievements. From a single carbon nanotube fiber to a structure stretching 96,000 kilometers into space, every stage of this project demanded extraordinary engineering precision. Autonomous factories, offshore platforms, orbital systems, and robotic climbers now operate as one integrated transportation network. Instead of relying on conventional rockets, cargo can travel continuously between Earth and orbit through a permanent engineering corridor. More than a technological achievement, the space elevator demonstrates how decades of innovation can reshape humanity's connection with space.
NextGen Machine Works, building the impossible. Subscribe to join the future.